Hey everybody, Trey here. Welcome back to another video. It's been quite a while since we've uploaded a video on the channel. As many of you know, I am a tour guide for a storm chasing tour company this year from about mid-April through the end of June, so didn't have a lot of time to upload videos during that time other than the occasional forecast discussion video on the morning of a given event. But that has ended for the season, and now I'm getting ready to get back on the video grind here on the channel. Starting with this one, in our 2023 tornado season forecast video, I'll put a link to that in the description below. By the way, we will be doing a video in the coming weeks, kind of analyzing our performance on that, how that forecast did this year. But in that 2023 tornado season forecast, I talked about we may see a return to the more typical areas that see tornadoes during the spring, places like Kansas, Texas, and Oklahoma. And Oklahoma certainly returned to the tornado spotlight this spring with a couple of very interesting events that occurred across the central part of the state. The first one on April 19th, and the second one on May 11th. April 19th, these were both localized tornado outbreaks across central Oklahoma. April 19th was had slightly more tornadoes in quantity and intensity as well. This was a very interesting event. A couple of different supercells. One produced a tornado near Tinker Air Force Base in Oklahoma City, and then the southern supercell produced a significant tornado in the town of Cole, Oklahoma, before moving off to the east and producing several more tornadoes near Etowah and eventually near Shawnee that produced damage. You see the Etowah tornado there on the left. May 11th was a similar but very different event as far as the meteorology goes. Yeah, but it was across a very similar area. Initial supercell produced a notable tornado near Newcastle, Oklahoma, before the southern supercell to the south produced another tornado in the town of Cole. Cole definitely took it hard this year. You can see there on the right panel, the Cole tornado did lots of damage in the southern portion of town, including lofting a roof off of a building. There was also a tornado in the town of Noble. So very interesting events here. Definitely brought Oklahoma back to the tornado spotlight after somewhat of a drought over the past couple of years, but definitely a return to prominence for Oklahoma as far as spring tornadoes go. So in this video, we're going to break down both of these events, starting with the April 19th event and then moving into the May 11th event. We'll compare and contrast the meteorology between the two. And then we'll go into some of the very unique tornado behaviors that occurred within these events, particularly with the April 19th event. Just a sneak peek, we'll be talking a lot about deviant tornado motion in this video. I was on both of these events. April 19th was just before tour season started, so I was out chasing with a couple friends and caught most of the tornadoes with that event from the southern supercell, including the one you see there on the left near Etowah, Oklahoma. And then the May 11th event, we were out on tour. Started the day in Goodland, Kansas, drove all the way down to south central Oklahoma and got on the tornado near Newcastle, and then dropped to the southern supercell to witness the Cole, Oklahoma tornado. So I'll be able to give you my perspective on both of these events from out in the field. And so this should be a very interesting video with some firsthand perspective for you guys. So without further ado, let's go ahead and get started. Let's start off with the April 19th event. You can see that cluster of tornado reports there in central Oklahoma, but you also see a few up from Kansas into Nebraska and Iowa. And that was actually the main target initially with this event. We take a look at our 6Z day one outlook from April 19th. We started off with a slight risk from Iowa down into Nebraska, Kansas, and then a very narrow slight risk along the dry line in Oklahoma. There was actually a 5% risk up from northeast Kansas into far southeast Nebraska, far southwest Iowa, northwest Missouri. So the main area for robust, sustained tornadic supercells was up in the northern portion of the risk area with just a 2% there, narrow 2% there along the dry line in Oklahoma. And they actually did add an enhanced risk up in that kind of Kansas, Nebraska, Iowa, Missouri confluence area there up to the north with a slight risk remaining there along the dry line. They did put in a 5% there along the dry line in Oklahoma at this 13Z outlook, but initially it was expected to be a very conditional risk along the dry line in Oklahoma due to some lingering capping that was a concern, as well as the forcing was expected to remain somewhat more focused farther to the north up into Kansas and Nebraska into Iowa. So and in the days leading up to this event, I was planning on chasing and really was focusing in on this northern mode as it appeared to be the more surefire mode. And the dry line was expected to remain very conditional in threat. And so the northern threat, the more surefire target, was a little bit more appealing. But as we got closer to the event, as I woke up on the morning of the 19th and went into the early afternoon, it became pretty apparent that the dryline in Oklahoma was going to put out some interesting activity. And the models were all over the place as well. Just as an example here, we'll take a look at the HRRR. This is the 12Z HRRR run from the morning of April 19th, and you can see not a speck of an echo there along the dry line in Oklahoma. We go to the 14Z run, starts to have some semblance of at least convective initiation there, just to the west of the Oklahoma City metro area in the early evening hours. So the models were really struggling. Some models were showing robust storms, and a lot of models were not, including the HRRR, until about midday or so. This is the 17Z run. Finally started to take a more robust setup started to take shape on the model there. You see a couple of robust supercells nearing the Oklahoma City metro area and just south on the 17Z HRRR. And just to show you how difficult a time the models were having with this event, this is the 18Z run. So the next run of the HRRR, you can see it pretty much takes that away. Tries to initiate some storms, not super robust though at all. So the models, especially the HRRR, was waffling back and forth on a solution here because of that ambient capping, some of the issues with the forcing, etc. But it did become pretty clear going to about midday into early afternoon that this was going to be an interesting event, perhaps a very volatile environment there along the dry line in Oklahoma, and we'll detail that in just a second. Supercells did eventually fire up with the first one down near Chickasha, rode up the I-44 corridor into the western portion of Norman, took on some pretty incredible mothership characteristics as you see here. This is my footage. Produced a very stout funnel cloud for quite a few minutes. As you can see here, just couldn't quite get it done, though, until it moved over to the eastern side of OKC, near Tinker Air Force Base, put down a brief tornado. At the same time, the southern supercell was getting its act together and eventually produced a significant tornado in the town of Cole. This is Reed Timmer's footage here of what was a very, very stout tornado that did some damage in Cole. You can see this is just really impressive footage. The storm itself also had some pretty crazy structure on it. We dropped south pretty quickly. You can see that just the bell-shaped structure from farther out. Just pretty incredible stuff there from this storm. You can see the time lapse here. At the same time producing the tornado, it clued off to the north and then would move into the eastern, just east of the metro toward the Etowah and Shawnee areas, producing a pretty noteworthy tornado near Etowah, as you saw there. Pretty noteworthy tornado, and then eventually the Shawnee tornado, which was a very powerful one and did some damage in the western portion of Shawnee. Initially, a tornado or two was expected here across Oklahoma. You can see down here a more conditional threat. This is the 6Z outlook, more conditional threat expected southward along the dry line into western and central Oklahoma. A tornado or two possible. A tornado or two turned into 18 different tornadoes near and just outside the Oklahoma City metro area. The orange contour here is the EF3 that went through Cole and Goldsby, and your Shawnee tornado up in here as well. A very large tornado that went through the western portion of Shawnee, with a couple notable ones in between, one that crossed I-35 here near Purcell, one near the town of Etowah out here, a few near the town of Etowah out here between Purcell and Shawnee, with a couple smaller ones in between. So a very prolific outbreak that had its origins in a setup that looked very conditional at the start. All right, let's dive into the meteorology behind the April 19th event. We'll start at 500 millibars as we always do, and right away your eyes are drawn to this big old trough situated across the western half of the continental U.S. Two different centers, it appears here. This is at 12Z, 7 a.m. Central Daylight Time. One center up here off the Pacific Northwest coast, one up here in the Montana-Wyoming border vicinity. Strong belt of flow rounding the base of this trough. And really, that strong belt of flow was providing a broad area of nice, subtle southwesterly flow aloft across the Central Plains as this trough inched its way east. And we've talked about it a lot on this channel. Whenever you see just broad southwesterly flow with little ripples embedded within that flow, that is usually a good sign for more subtle forcing and more discrete development. You do see a few different ripples here out amongst this broad area of southwesterly flow, rounding the base of this trough, and so that was an eye-catcher for me, at least looking at the early stages of this event. Now, it was mentioned that the forcing was a little bit stronger farther to the north, obviously Nebraska, Kansas, a little bit closer to the main core of at least the eastern core of this jet streak here. And as we go through the afternoon on the 19th, it's a little bit difficult to tell where the strongest forcing is. We can use a product called vorticity and vorticity advection here. You can find this on the SPC mesoanalysis pages. Keep your eye on just the color fill of this map. I won't go too deep into the nuances of this map, but just focus on the color fill, the greens, yellows, and oranges here, which is the measure of vorticity or spin in the atmosphere. Usually, strong troughs, short waves are associated with enhanced spin in the atmosphere, and that can help improve the chances for storm development in a given region. So you'll notice here, as we go through the afternoon on the April 19th, we start to see a little bit of a lobe there in northern Oklahoma, southern Kansas, making its way into eastern Kansas there, and also a nice lobe of vorticity up there into Nebraska. Not a whole lot to show in Oklahoma. We do have a little bit of a shortwave, however, that was apparent going into the afternoon on the 19th. So keep your eye there on the Texas Panhandle. This is at 20Z, so 3 p.m. Central Daylight Time on the 19th. We do see a little bit of a kink in the flow there, moving into the Texas Panhandle in western Oklahoma. That may have very well helped initiate storms there in central Oklahoma, even though the overall forcing was extremely subtle and fairly neutral overall. But of course, the background large-scale forcing for ascent is not the end-all, be-all. We can have other features, such as surface convergence zones, etc., which we'll talk about in a second, that can help overcome neutral to very subtle forcing in the large scale and actually initiate storms in a given environment. Let's go down to 850 millibars. Now, the core of the 850 millibar cyclone was well off to the north in the vicinity of the core of the 500 millibar trough up there in that Montana region. But it was a very broad 850 millibar cyclone. You can see the closed contours extend all the way down here into the central and southern plains, down into the Texas Panhandle and Oklahoma. And given that we had a nice broad belt of southwesterly flow traversing the Rockies, we were expecting some semblance of consolidation of the low-level cyclone here in the eastern Colorado vicinity come the afternoon, and that's exactly what happened. We go forward with time here, and you can see a nice center of that 850 millibar cyclone becomes evident there by late afternoon. This is at 22Z, so 5 p.m. Central Daylight Time. Nice closed contour there in southeast Colorado. Evidence of the consolidation of that core of the 850 millibar cyclone down there as a result of the Lee cyclogenesis process. We started the day off, as far as the low-level jet goes, with a nice 25 to 30 knot low-level jet or so out across the plains. That would maintain itself throughout much of the day, but as that cyclone developed there in southeast Colorado, we started to see a little bit of an increase in the low-level jet farther to the south, 35, 40 knots or so, and then eventually after dark, a real stout increase there. This is at 4Z. We see up to 50, 55 knots out here, out across Oklahoma. So a nice, modest, and increasing low-level jet with time throughout the day really set the stage for the environment to become conducive to tornadic supercells, of course, if storms were to fire. Now, I want you to keep in mind the direction of this 850 millibar flow, and we're going to come back to this in a second, but mostly southwesterly, south-southwesterly to southwesterly across Oklahoma throughout the day on the 19th. We're going to come back to this in a second. This was a major factor in why we were actually able to get storms to initiate across Oklahoma and along the dry line in the afternoon on April 19th. But first, we'll go ahead and look at the surface. So here's our surface pattern to start off the day on the 19th. This is at 12Z, 7 a.m. Surface low center up here in that Montana, North Dakota vicinity, with another center up here in the Kansas-Nebraska border area. This was going to be another impetus, another reason why the northern mode was going to be a favored location for storm initiation in this environment. You had a little bit more oomph, if you will, from the surface low, a little bit more backed winds, a little bit more surface convergence there, right along that surface low, and just ahead of it, and there in southeast Nebraska, northeast Kansas, whereas down to the south, we were a little bit farther removed from any surface low center here across Oklahoma. But again, that was to change throughout much of the day as we were expecting surface low development, at least consolidation of a surface low center there thanks to the Lee cyclogenesis process in southeast Colorado. You see as we go through the afternoon, we start to get a nice deepening surface cyclone there. This is at 21Z, so 4 p.m., a nice 996 millibar cyclone there out across southeast Colorado, helping to tighten that dry line across Oklahoma, really strengthened those surface winds. Already some strong gradient winds up from the northern plains down into the southern plains as those that pressure gradient very strong. Those isobars really packed tightly there. So strong low-level winds helping to really transport that surface moisture in out ahead of that surface low developing in southeast Colorado. Eventually that surface low would move off to the east very, very slowly. But we were relying on the dry line mostly to initiate storms in this environment. Now let's take a look at some surface data here, our actual surface data. So we'll start out at 12Z, or 13Z, so the morning of the 19th, and you see already a broad area of 60s, upper 50s to 60s surface dew points out across the region. Oklahoma City at 65 over 59 there, with your, of course, higher dew points situated in central to southern Texas, mid 60s dew points down there. Those would advect their way northward throughout the day, given that strong pressure gradient there at the surface. Those winds backed out of the south or south-southeast, pumping that low-level moisture northward into the region. And we're going to take a look at some soundings here in just a second. As we go through with time, though, you can really start to see that dry line take shape. I'm going to go out to about 21Z here. Makes it a little bit easier to ascertain where the dry line is here. So if we were to draw in our dry line, you see dew points very, very low out to the west across the Panhandle, single digits out there across the Texas Panhandle, increasing just slightly to the 20s and 30s out here across western Oklahoma, whereas we have 60s dew points out here across central Oklahoma. Also, you see a wind shift here, winds out of the southwest across western Oklahoma, more southerly there out across central Oklahoma. So definitely the dry line boundary was somewhere in this vicinity right here. If we were to draw that boundary, it would be something like that, of course, stretching up into Kansas, but we'll focus, of course, on our Oklahoma target here for now. So notice the orientation of the dry line. Definitely across central to southwest Oklahoma, it was definitely more northeast to southwest oriented. That's going to be really important. I told you to remember the direction of the 850 millibar winds. So here's our 850 millibar winds, right? So our wind barbs definitely more so out of the south-southwest to southwest, and our 700 millibar winds much of the same as well. More out of the southwest as we went into the afternoon, definitely more southwesterly winds there. So our mid-level winds, 850 to 700 millibar winds, were definitely out of the southwest. Now, I've heard a lot of gripes from storm chasers in the past about slanted dry lines, and that oftentimes those gripes are correct. Oftentimes you'll have shear vectors that are more parallel to that initiating boundary when you have a northeast to southwest oriented dry line. When you have southwesterly upper level winds, your shear vectors can be very much parallel to that dry line or initiating boundary, creating a more messy storm mode. But in this case, the slanted nature of the dry line actually helped things out. So if you'd imagine on a normal north-south dry line, let's say we have a north-south oriented dry line, perfectly north-south. Of course, we have surface convergence along that dry line, so storms are likely to go up on the dry line. Well, if we have southwesterly 850 millibar and 700 millibar winds, those storms are going to go up on the dry line, but they will be able to move off the dry line pretty quickly. And if you have an environment that is somewhat capped, the updrafts may struggle as they move off the dry line. The dry line, remember, is not just a fine line of surface convergence. It's actually a zone of ascent, a dry line circulation that develops. So it extends upward into the atmosphere and is a large zone of favorable ascent for these updrafts to take advantage of. So let's say we have a slightly capped environment, again, on a north-south oriented dry line with southwesterly mid-level winds. Those updrafts are going to go up on the dry line, but they're going to be pushed off the dry line as they encounter those mid-level winds that are going to push them off to the northeast. And so they may struggle with a little bit of remnant capping in the atmosphere, as we had on the 19th, a little bit of capping still in play at this point in the afternoon. Now, if we have a slanted dry line like we had on April 19th, now when you have southwesterly 850 millibar and 700 millibar winds, those updrafts are going to go up along the dry line, but they will be able to stay in that zone of ascent associated with the dry line for much, much longer. Therefore, they will be able to sustain themselves for quite a bit longer, and they have a better likelihood of becoming more robust supercells in a given environment. And that's exactly what happened on the 19th. We had a nice slanted dry line here. Let me draw this again for clarity. So our dry line's something like that. You had updrafts that went up along the dry line, still in maybe a slightly capped environment, but because the 850 millibar winds and 700 millibar winds were out of the southwest, they were able to move those updrafts, but keep them in that zone of ascent along the dry line for much, much longer. And as a result, that was a major factor that was able to allow storms to fire and sustain themselves in central Oklahoma on this day. If we had a north-south oriented dry line, those storms may have struggled with a little bit of that remnant capping in place across the region. So that was an interesting factor with this event that really, one of the main factors that allowed storms to really foster and flourish in this environment was that you had them go up on the dry line. They were able to stay in that zone of ascent and dry line circulation for a lot longer, and therefore sustain themselves into nice, robust tornadic supercells. Now, of course, there is that concern of a more messy storm mode. We already have checked the box for a kind of subtle forcing regime in the background that may help favor discrete storms in this mode. Let's take a look at our shear vectors with respect to the initiating boundary. So if we go to our 0 to 6 kilometer shear vectors here, we go forward, you'll notice that they are pretty much due westerly, so very much off the dry line. Even though we had quite a slanted dry line here across southwest Oklahoma, those shear vectors are almost due westerly, and therefore they had a pretty solid angle of perpendicularity between the initiating boundary and those shear vectors. So even though the dry line was slightly slanted, we were still able to favor a discrete storm mode. That plus the overall fairly subtle forcing regime allowed for a discrete storm mode to be the main storm mode for this event. Now, we had, as we talked about, the southwesterly mid-level winds helping to keep those storms in the dryline circulation for longer, helping to sustain robust storms. Another thing was that we were able to reach convective temperature pretty easily. Some of the guidance, of course, guidance like the NAM that likes to be way too cool at times, showed that the temperatures may not get up into the mid to upper 80s, which is what we needed to get to in order for storms to reach that convective temperature. We've talked about the convective temperature before. It's that temperature that the air parcel at the surface needs to be heated to in the absence of large-scale forcing mechanisms in order for that surface parcel to begin to rise on its own. And we'll take a look at a more deep analysis of our soundings here in just a second. But here's our 12Z Norman sounding. Our convective temperature was 92 degrees. So that just means that if we were in the absence of all other forcing mechanisms, shortwave troughs, surface boundaries, etc., that surface temperature would need to warm to 92 degrees in order to allow those surface parcels to rise on their own. Now, by 19Z, when we put up our second Norman balloon, our convective temperature was at 83. Of course, we had the additional influence of that incoming shortwave and the main trough coming in. That helped to lift and cool the capping inversion. Again, we'll talk more deeply about the soundings and the thermodynamic environment in a second. But our convective temperature was 83 at this point. We can go back to our surface map. Again, this is at 4 p.m. Central Daylight Time. You can see we have well exceeded that 83 degree temperature all across central Oklahoma, right along and just ahead of the dry line. OKC at 86, Fort Sill there near Lawton at 89 degrees. So even our initial 92 degree convective temperature was getting close to being breached, especially west of the dry line. It had been breached here out across northwest Texas. So the fact that we were heating very well into the upper 80s, the fact that you had our mid-level winds parallel to that dry line, allowing updrafts to stay in that zone of ascent for much longer and sustain themselves, these two factors really made it become clear that we were going to see storm initiation across southwest and central Oklahoma come the mid to late afternoon hours on the 19th. Now, of course, the drawback to it warming up this much was that the temperature dew point spreads were a little bit on the high side initially as storms fired. Oklahoma City 86 over 62. Of course, we've talked about this before. We like to keep it right at or below that 20 degree Fahrenheit temperature dew point spread as kind of your upper echelon, upper limit for tornadic activity. It was a little bit better down to the south, 82 over 64, slightly better moisture, still working its way into central Oklahoma. So given that little bit high temperature dew point spreads, plus the fact that low-level shear was still a little bit weak as storms initiated, meant that the supercells, now that we'd figured out that storms were going to fire, we're probably going to have a little bit more of a hail threat initially, and then transition to a tornado threat as temperature dew point spreads went down and low-level shear increased going into the early evening hours. You see here, we eventually do get that better moisture up into the area, 66, 64 there, up toward OKC. Temperature dew point spreads a little bit on the lower side there, about 16, 17 degrees there across central Oklahoma. So as temperature dew point spreads came down, low-level shear increased, which we'll take a look at in just a bit with our sounding analysis. And we were able to get a transition to more of a tornadic hazard over a hail and wind threat. Let's take a look at a few observed soundings. The NWS Norman office released balloons at 12Z and 0Z. They also released a midday balloon at 19Z. Right now, we'll just look at the 12Z and 19Z observed soundings. We'll save that 0Z sounding for our more in-depth sounding progression and analysis coming up in just a little bit. So here's your 12Z Norman, Oklahoma soundings of 7 a.m. Central Daylight Time. A couple things are pretty obvious right off the bat. There is a pretty solid moist layer. It's not very deep, but it's not very shallow either. So decent moist layer beneath a very strong elevated mix layer here. You can see that very deep layer of steep lapse rates aloft with that very dry air here as that dew point line juts off well to the left there. So a very stout elevated mix layer. We talk about the EML almost every video on the channel here. The EML, or elevated mixed layer, is that layer of warm, dry, well-mixed air that originates on the higher terrain of the desert southwest, western Mexico, and gets transported to the east on the mid-level winds, and gets situated atop that moist layer in the low levels, and that can help prohibit storm formation through much of the day in a given environment and allow instability to build throughout the day. We already have decent instability here at 12Z, about 1,000 joules per kilogram of mixed layer CAPE. But very, very capped. That's why our convective temperature was 92 degrees here on this 12Z Norman sounding. Again, that convective temperature is that temperature that the surface must warm to in order to allow surface parcels to rise freely on their own without the help from external forcing mechanisms that would help cool and lift this elevated mix layer. We had that in place. That shortwave trough moving in was able to help cool that elevated mix layer, as you'll see on the 19Z sounding here, and allow that cap to erode fairly nicely going into the early afternoon hours. You see a much less evident cap here. Still some pretty dry air there aloft, but by 19Z, 2 p.m. Central Daylight Time, that moist layer had deepened just slightly above about 850 millibars there beneath a very rapidly eroding cap. You don't see as much convective inhibition there. Almost negligible at this point by 19Z. Just needed a little bit extra cooling aloft there, a little bit extra forcing to allow those storms to push through that remaining cap, which was provided by the strong convergence along the dry line, strong surface heating. A little bit of an inverted V profile there, a nice well-mixed boundary layer. Still, temperature dew point spreads within that 20-degree mark, 82 over 64 there at Norman at 2 p.m. So a little bit high, but still manageable within that 20-degree threshold there. You'll notice here that the hodograph by 19Z, deep layer shear increasing from about 30 knots at 12Z to 35 knots here at 19Z. So hodographs lengthening just a little bit of curvature there in the low levels, a little bit of veering of those low-level winds with height there at 19Z. But overall, fairly weak low-level shear, adequate deep layer shear, strong instability there thanks to that elevated mix layer and strong surface heating. And that was a recipe for some fairly initially high-based supercells with mostly a large hail threat. You'll see here the initial storm near Blanchard, Oklahoma. This is my time lapse here. You can see that storm a little bit high-based and began to drop some pretty large hail there, as you see here in this video. So initially, the hail threat was going to be greatest with these storms, but then as the low-level shear increased later into the afternoon, along with this rapidly eroding cap and strong instability, the tornadic threat increased pretty rapidly going into the early evening hours, which we'll show here in just a second. Here's our visible satellite imagery starting at 14Z on April 19th. First off, you see some of these cloud streets here across central Oklahoma, indicating some low-level stability, but that would burn off nicely throughout the day into the morning and early afternoon. You see here, by about midday or so, full surface heating ongoing across all of the western half of Oklahoma. That allowed those temperatures to really soar into the mid to upper 80s and get that instability to build and that cap to erode. Now you see this plume of high cirrus coming in from the west. This is at 1821Z, so just after 1 p.m. Band of high cirrus, or a plume of high cirrus coming in from the west. This was associated with the ascent coming in. So the cirrus was associated with that shortwave trough moving in. And you'll notice as that ascent moves in, as that band of cirrus moves in, you start to see some agitated cumulus underneath, especially here in northwest Texas where temperatures got a little bit hotter, breached those convective temperatures first. But also we had some bubbly cumulus out here along the dry line in southwest Oklahoma. And that area would be our favorite area for storm initiation going into the late afternoon. This is about 4:30, first initiation attempts along the dry line there. along the I-44 corridor just to the south and southwest of Chickasha. A couple moved up into the Oklahoma City metro area, but this middle one, I believe, was our first attempt at our tornadic supercell that moved into West Norman and eventually produced that brief tornado near Tinker Air Force Base. And then back here to the southwest along the dry line was our eventual Cole, Oklahoma cyclic tornado producer. You see some very strong overshooting tops with these storms. Very impressive satellite imagery here as we got into the early evening hours and our tornadic threat really started to increase. Just a quick look at the broad view of the radar before we dive in a little bit closer. This is the radar starting at about 3:30 p.m. You see our initial attempts just after 4 p.m. Central Daylight Time there from just west of the Oklahoma City metro area. KTLX radar is right there, so OKC is right in here. Just west of the OKC metro down into southwest Oklahoma along the dry line. And that middle cluster would actually become our first attempt at a tornadic supercell here. That would become the Tinker Air Force Base tornado producer there. And then you can see the supercells to the southwest. That out of that cluster, that would emanate the Cole to Shawnee cyclic tornado producer. As you see there, you see that southern storm kind of merges there into one and then takes a pretty abrupt turn to the east. The initial storms were moving much more off to the northeast, especially these ones. These were left splits off the original cluster of storms, moving off more to the northeast. But this one took a pretty abrupt turn to the east and took a much more easterly track toward Cole and eventually Shawnee, although the tornadoes themselves took some pretty interesting paths, which again we're going to dive into in just a bit. All right, let's go through a progression of RAP model soundings in proximity to the tornadic supercells on April 19th. These have all been taken from the town of Purcell, about 30 minutes south of Oklahoma City and just south and southeast of the track of the southernmost supercell on April 19th, the Cole to Shawnee cyclic supercell. So a pretty good representation of the environment in the inflow region and in very near proximity to these tornadic supercells. So we'll go from about 12Z through the evening hours, about 4Z. We'll start off at 12Z here. We've already talked about the initial conditions associated with this environment on the morning of the 19th. We had somewhat of a moist layer there extending up to about 850 millibars beneath a very stout capping inversion. You see that steep lapse rate plume there extending all the way up above 850 millibars for quite a ways along with that dry air. Again, that's associated with that elevated mix layer atop that moist layer near the surface. We also have some decent curvature to start off with in the low levels of the hodograph. You see there a little bit of clockwise curvature there, a little bit of veering of those winds with height. That is typical, and we would lose that a little bit throughout the day because the low-level jet does act on somewhat of a diurnal cycle. It tends to increase nocturnally, and come the daytime, it tends to decrease a little bit unless you have very strong low-level response associated with the given event. We did not have that yet, as we discussed. That surface low is still in the process of developing out to the west in eastern Colorado, so we would lose a little bit of that hodograph curvature throughout the day. And low-level shear would in turn decrease. So we'll go through, and I want you to keep your eye on the capping inversion here as we go into the early afternoon hours. So we go through 13, 14, 15Z, and we start to see a very stout decrease in that capping inversion. This is at 20Z, so 3 p.m. Central Daylight Time, right before storms initiated. So a couple things we noticed. We did see a little bit of a deepening of that moist layer, just above 850 millibars now, as we saw on our observed sounding from Norman, Oklahoma. We see that cap has very much decreased here, and we're almost purely uncapped. Mixed layer SIN, convective inhibition, only at about minus 12. That is really negligible at this point. And with the fact that we had strong surface convergence along the dry line, strong surface heating, those temperatures had warmed up into really the mid-80s there in central Oklahoma. That was, and the approach of the shortwave as well, helping to cool these mid to low levels. We were starting to see a very rapid erosion of that cap, and it was, again, becoming very apparent that we would see storm initiation along the dry line by mid to late afternoon. This is at 21Z, 4 p.m., and you can see that that capping inversion has pretty much gone to zero there. Mixed layer SIN basically at zero, -2. That is negligible, and at this point, storms were ready to fire along the dry line. You'll also notice that low-level shear had weakened somewhat. I'll go back a couple of soundings here, and you see low-level shear had very much decreased throughout the day. This is at 17Z, so midday. Very minimal curvature there in the low levels. And watch what happens to those low-level winds, though, as we go into the early evening hours. And that hodograph starts to really jump up. This is at 22, 23Z. Watch what happens by 23Z. The surface winds had backed, and the low-level winds had strengthened a little bit. Our low-level jet had jumped from, say, about 25 to 30 knots or so at about midday to about 35 to 40 knots almost at 6 p.m., 23Z here. And our hodograph, take a look at this sounding. This is a pretty classic textbook sounding for tornadic supercells in Oklahoma. You can see our cap had eroded fully, 80 over 66. We continue to see that low-level moisture advection as those dew points continue to climb a little bit into the early evening hours. And we were fully uncapped, lots of instability to deal with, 3,500 joules per kilogram of mixed layer CAPE, so a very unstable environment. If you couple that with strong deep layer shear for supercells, our effective bulk shear almost at 50 knots, so long hodographs, favorable for supercells. We'd already talked about the discrete mode that was likely with these storms. And take a look at that hodograph, that low-level hodograph especially. That is pretty darn impressive. I'll show you our 0Z Norman observed hodograph as well. This balloon actually popped, probably in the anvil of one of these supercells. So we didn't get a full representation of the environment but we got plenty of information to analyze, and you can see here a very similar looking profile on the observed data, 78 over 65 there at the surface. Again, this is at 7 p.m. on April 19th, fully uncapped there with lots of buoyancy. And just look at that hodograph. That is almost pure streamwise vorticity in the lowest levels of the hodograph. We've talked about streamwise and crosswise vorticity before on the channel. Streamwise vorticity is when you have your storm relative wind vector drawn from our storm motion vector to the level of the hodograph that we're interested in, and our horizontal vorticity vector, which is parallel or perpendicular and to the left of the hodograph. When those two vectors are parallel to each other, we have what's called streamwise vorticity. You can think of it as an NFL quarterback throwing a football with that perfect spiral. It's a lot easier for the wide receiver to catch. In the environment of a supercell, when the supercell is ingesting streamwise vorticity or spin like this, it's ingesting that spin, and it's already perfectly oriented to be tilted into the vertical and become a possible tornadic circulation eventually. When it's crosswise, meaning that these two vectors are perpendicular to each other, that's like a quarterback throwing a football it's wobbling. It doesn't have that perfect spiral. It's a lot harder to catch. So in a storm sense, if a storm is ingesting crosswise vorticity, the storm has to manipulate that quite a bit for it to become favorable for tornadogenesis in supercells. We'd much rather prefer to see streamwise vorticity like this in supercells. That makes it a lot easier for storms to become tornadic when they ingest this streamwise vorticity. And here you can see all the way up through the lowest levels of the atmosphere, lots and lots of almost purely streamwise vorticity, especially in the very low levels there of the hodograph. So a very favorable looking environment for tornadic supercells here. Again, we transitioned from what was early on a hail threat. You can see here at 20Z, 21Z, just before storm initiation. We had a little bit higher bases, 83 over 64, still within that 20-degree temperature dew point spread, but a little bit higher storm bases. But we had lots of instability with fairly weak low-level shear, sub 150 meters squared per second squared effective storm relative helicity. So weaker low-level shear, strong deep layer shear for supercells, and favorable instability, strong instability in the mid-levels of the atmosphere near that freezing level. That is a recipe for large hail, and as we saw, those storms initially produced some pretty large hail before that low-level shear really started to ramp up by 5, 6, 7 p.m., and we started to see this streamwise vorticity ingestion into the supercells, and we transitioned from a hail threat to more of a tornado threat going into the early evening hours. We continue on past 0Z, and you can see that the hodographs just continue to get bigger and bigger. This is at 2Z, 3Z, 4Z, so 11 p.m. here, and you can see that the hodograph is just pretty ridiculous at this point. 56 knots of deep layer shear, favorable for supercells. At this point, the event was kind of winding down, but still tornadic activity was possible, and you can see why. Incredible veering and strengthening of those low-level winds with time. That low-level jet had jumped up to about 55 knots or so here, basically up from about 25 knots or so early in the day to about the start of tornadic activity, about 30 to 35 knots or so, to now about 50 to 55 knots. Pretty impressive jump in the low-level jet there. Still lots of streamwise vorticity there in the low levels, and lots of veering of those low-level winds with height. Even though the cap started to build back in just a little bit as we lost surface heating going into the evening hours, we still had tornadic activity well into the evening, especially toward the Shawnee area. So very interesting progression with those soundings there, and you can see why. Just an absolute classic look for a tornadic supercell environment with the sounding. Strong instability, strong low-level moisture with very strong streamwise vorticity ingestion in the low levels, strong veering of those low-level winds with height. over 300 meters squared per second squared of storm relative velocity with about 3,500 joules per kilogram of mixed layer CAPE. That is an upper echelon environment for tornadoes, and no wonder we saw some pretty impressive storms, tornadic supercells, with this event. We'll talk about some of the more nuanced aspects of the wind profiles and hodographs of the April 19th case when we compare it with the May 11th case, for example, precipitation venting, supercell size and shape, etc. But one of the more notable, perhaps the most notable aspect of the April 19th case was the significant deviant motion of especially the more notable tornadoes. So your EF3 Cole to Goldsby tornado, extremely deviant motion there you see off to the north, even northwest almost at the end, as well as the Shawnee tornado, and then a couple of the ones in between as well. They displayed some very interesting behaviors as far as deviant motion goes. And we can use the KTLX radar data, the Oklahoma City radar, to really illustrate the deviant motion with these tornadic circulations. So on the top left is reflectivity, top right is velocity, and bottom left is correlation coefficient, bottom right is differential reflectivity. I want you to pay attention mostly to the reflectivity and the velocity here, because those will really show you the deviant motion with these tornadoes. So supercell fires up southwest of Chickasha, and then really starts to take shape as it approaches Blanchard and eventually Cole. So there's our first tornado there. As it goes through Cole, does some damage in the town of Cole, and I'll back it up here. Just keep your eye on that velocity signature and the hook echo on reflectivity. Just absolutely impressive here that it goes almost back due north and then even due northwest at the end. You see right there, goes off to the due north and then almost back to the northwest there at the very end. So very impressive tornado behavior with that first tornado. And then we continue to see that deviant motion throughout the event. See multiple tornadoes here occlude off to the north and northwest until the supercell met its demise out to the east of Shawnee. So very impressive data there. And as we've done before, we can use a hodograph technique pioneered by Cameron Nixon and John Allen to determine the deviant motion from our hodographs. I'll put a link to Cameron's article on deviant tornado motion here in the description box below, as well as the journal article Nixon and Allen 2021 that describes this hodograph technique. So we're going to use our 23Z 6 p.m. Central Daylight Time RAP proximity sounding from Purcell that we saw just earlier. And then we'll go ahead and do our deviant motion technique. So the way we calculate or determine our deviant motion is we first take the mean wind in the lowest half kilometer or 500 meters of the atmosphere. The SharpEye soundings, the software that is used to plot these particular soundings, makes it very easy for us. This pink line here is the wind shear vector in the lowest 500 meters of the atmosphere. So we basically just take the center point of that line. We then plot our storm motion vector. Here we'll for simplicity's sake, use our bunkers right storm motion as predicted by this hodograph. And then to find the deviant motion vector, you take the midpoint of those two, take the average of those two, and then draw your vector from the origin. So this would be our deviant motion vector. So you can see that our storm motion vector, I'll draw that in blue here, was much more northeasterly, while our deviant motion vector, deviant tornado motion vector, was almost due southerly, basically out of the south, maybe just barely east of due north. So this was very much expected that tornadoes would be deviant on this day. Also, storm motion was about 25-30 miles per hour. Slower storm motions tend to have more deviant tornadoes. Faster storm motions kind of mask the deviant tornado motion. So you don't often see that when storms are moving 50, 60, 70 miles an hour. But when you have slower moving storms like we had on April 19th, you will see deviant tornado motion. You can see by our deviant tornado motion vector right there, almost due southerly from south to north, maybe just east of due north, that this was very well predicted. And we'll take a look. So our deviant tornado motion vector looks something like this. And you'll see that those tornadoes did exactly that. We'll go back, I'll back it up to the Cole tornado, and you can see here, I'll play it again. That tornado moves off to the east with the storm motion initially, and then starts to take a turn very much off toward the north in the latter portion of its life cycle. I'll continue the animation here, you can see that. And then maybe, perhaps back to the northwest, perhaps a little bit of advection around or orbiting around the parent mesocyclone. That can happen sometimes when you see tornado paths that look like this, when they have a little kink at the end. Sometimes this last part will be orbiting around the parent mesocyclone, while this will be the advection by the storm relative wind, or aka our deviant motion technique that deviant motion vector that we found. So it was definitely, and I remember when forecasting for this event beforehand, figuring out where to chase, I actually did this technique with some of the model forecast soundings that I saw, and we predicted that tornadoes very well may be deviant on this day. And so we knew that we may not want to be north of these tornadoes, especially as they started to occlude. And exactly what we thought was going to happen did happen. Our deviant tornado motion took place, as you can see there by the Cole tornado, and then the multiple tornadoes after it, especially these ones there as well, occluding off to the north and even northwest, given our deviant tornado motion vector almost due southerly. All right, let's shift gears into the May 11th event. We won't go into as much depth with this event as we did with the April 19th event, because the April 19th event was definitely, in terms of quantity and intensity of tornadoes, more impressive than the May 11th event. But May 11th still holds some pretty interesting meteorological information for us to dissect. So let's go ahead and get started with that. May 11th started off as a large enhanced risk from the Colorado-Kansas border down into much of the central portion of Oklahoma, with a large 10% tornado risk coincident with that enhanced risk, and even a 10% hatched area for the Oklahoma portion of the outlook. So strong tornadoes were certainly a possibility with this activity. Eventually, the two areas were split into two. Large enhanced risks still remained, but two separate 10% areas existed on that day, western Kansas, and then one down in central and southern Oklahoma with that 10 hatched area remaining. And as you can see here, we have those two separate areas of tornado production there up in northwest Kansas, which was more of a cold core type setup. Of course, not going to touch on that in this video as we're focusing on the Oklahoma portion of these risks, and you can see the numerous tornado reports there in Oklahoma. 9 tornadoes were documented across central Oklahoma on May 11th, most of them weak and short-lived, with the exception of a couple here to the south of the Oklahoma City metro area, including one, an EF1, that went through a very similar path as the April 19th tornado near Cole and Goldsby, and one that went through the town of Noble, just south of Norman. We were able to chase that day, as I said, and we captured the Newcastle tornadoes here. Very nice cone tornado there that made contact with the ground a couple of different times, and then eventually we were able to witness the Cole tornado basically from birth, watched as it came closer to us, and was quite a long-lived tornado, and as it came closer to us, unfortunately, was able to take the roof off of a building. As you see here, some nice multiple vortex action there, and you'll see here that it starts to unfortunately do some damage and rips the roof right off of that building right there. So pretty impressive tornado there. And also the Noble tornado, one of my friends, Kevin Rolfs, was able to catch that tornado as it moved across town there and did some damage. So let's dive into the meteorology behind the May 11th event. We'll start out at 500 millibars once again, and right off the bat you see a very substantial difference between the April 19th case and the May 11th case. For the May 11th case, we had a very compact trough here, very tight vorticity center or center of spin here impinging into the southern plains, whereas in the April 19th case we had a very broad sprawling trough here, even two different centers taking up pretty much the entire western half of the continental US. And that not the case with the May 11th event. Very compact cyclone here at 500 millibars, with centered here across the Colorado-New Mexico border vicinity, and a very tight, compact, but very strong belt of enhanced flow rounding the base of that trough. If we go up to 300 millibars as well, you'll see that very strong defluence aloft, the spreading apart of those wind vectors in the upper levels of the atmosphere. We've talked about this before. When you have the winds spreading apart in the upper levels of the atmosphere, that leaves a void, and Mother Nature doesn't like that void. So what it tries to do to compensate is bring air up from below to fill that void, and that's how you get large-scale rising motion for ascent in a given setup. So very strong defluence aloft, and this trough was forecast to eject into the southern plains, very favorably timed as the dry line was situating across Oklahoma, favorably timed with diurnal heating, and you can see here that it does that. Now, one interesting facet of the cyclone here associated with the May 11th event was that it was vertically stacked, which means that the center of circulation, we'll use 12Z here as an example, was basically, as we know, first of all, as we know, cyclones extend through the atmosphere. They're not just at one single level. So for a typical cyclone that is maturing or mature, usually you'll see it tilted back toward the west or northwest with height. So for example, the center of the circulation at the surface would be there, your mid-level center would be there, and your upper-level center would be there. So you have a vertically tilted cyclone. That means the cyclone is maturing, or it is mature. We'd like to see that we usually see that with our broad, our stronger troughs here in the springtime in the plains. And for the April 19th case, not the best example, but I'll show that here, that we had somewhat of a vertically tilted cyclone. Center of circulation at 500 millibars here, somewhere in southeast Montana. As we go down, we'll go down to 850 millibars. You see the circulation over here at the North Dakota-Montana border. So some semblance of tilt there as you went upward in the atmosphere back to the west with that cyclone. Means that it was somewhat in its maturing phase or was a mature cyclone at that point. The May 11th case, not so much. You'll notice here, as we plot our 500 millibar center right there at the Colorado-New Mexico border, let's go down to 700 millibars. You see it's pretty much in the exact same spot. We'll go down to 850 millibars as well. And you see that right there, our center pretty much in the exact same spot, right in there in far southeast Colorado, and then our surface cyclone was basically in the same spot as well. So you can see here we have a pretty vertically stacked cyclone. That tends to mean that the cyclone is past its prime, if you will. It's on its decaying phase, and we saw that with the 500 millibar trough in particular with this event. You'll notice here that it kind of gets sheared out, starts to eject off to the east or east-northeast, and kind of gets closed off and weakens quite a bit as we go into the evening hours and into the early morning hours of May 12th. So interestingly, that allowed the upper level winds to somewhat weaken with time, and you'll see that as we go through our hodograph discussion a little bit later, that the upper level hodograph was quite weak, and that had some implications on what forecasters were thinking as far as the supercell mode with this particular environment. Still a very strong trough, strong defluence aloft, strong spin there associated with this trough and lift. So we had a very favorable look for severe storms as that trough moved to the east or east-northeast into the afternoon. Here you see a belt of nice 50, 60 knot flow there impinging into western Oklahoma where the dry line was setting up, which we'll show here in just a second. Now, as you might expect, given a little bit more compact trough in a much better position to initiate Lee cyclogenesis, we would expect to see a stronger low-level response, at least initially, than what we saw with the April 19th event. And that's exactly what we had. We had a very well-defined cyclone here centered across southeast Colorado already. If you recall the April 19th event, we were kind of waiting for that initial low-level response to take place. It eventually did during the afternoon hours and helped really ramp up the environment across to its east across Oklahoma for that event. This one, we already had the low-level cyclone in place, moving off to the east just a little bit with time, really just kind of meandering, if you will. But you'll notice here that the low-level jet didn't get all that strong with this low-level cyclone here. We start off the day about 10 to 15, 20 knots or so out to the east of that. And across Oklahoma throughout much of the day, we maintained that somewhat range of about 20 to 25 or so knots of flow there across Oklahoma there at 850 millibars. That's not a value that you typically would associate with strong tornadoes. Usually we'd like to see that low-level jet in the 30s, 40s, 50s plus to really ramp up those low-level hodographs, get that low-level shear going. This was likely the result of the weakening of the upper-level trough as it ejected into the plains. As you might expect, because the upper level, what happens in the upper levels is tied to what happens in the lower levels, a weakening trough in the upper levels would probably mean a neutral or weakening response in the low levels. So generally, if you have a big trough moving in, taking on a much more negative tilt as it ejected into the plains, becoming more mature, you'd get a much more mature low-level response. But because we had that upper-level trough decaying a little bit as it moved into the plains, we weren't really seeing that strong cyclogenesis in the lee of the Rockies, so those low-level winds were not able to really ramp up as they might in a typical tornado outbreak scenario. But as you'll see, we did have enough curvature in the hodographs, given somewhat southeasterly surface winds with basically due southerly 850 millibar winds, and then of course the deep layer shear was favorable for supercells as we had those veering winds in the low levels with more southwesterly flow in the upper levels. So even though we had a more modest low-level jet that really never ramped up significantly, you see here at about a 4Z, so closing in on the 11 p.m. hour Central Daylight Time, we did try to ramp up to about 30 knots or so, but by then storms were basically on the outs, and the main portion of the event took place with this low-level jet that was somewhat modest by springtime standards in the southern plains. We'll go down to the surface here. Similar look to the surface pattern. Surface low already had developed here across the Colorado-New Mexico border vicinity there just northwest of the Clayton area. Again, that would basically sit there, maybe meander slightly to the east with time. You'll see those winds in the low levels nice and backed because of that low-level flow feeding up into that well-defined surface cyclone there in southeast Colorado. A potential fly in the ointment that became pretty apparent on the morning of May 11th was ongoing convection across southern Oklahoma. This is some radar imagery starting on the evening of May 10th, so the day before the May 11th event. You can see all this convection in southeast Colorado and eastern New Mexico eventually congeals into an MCS that makes its way through the Texas Panhandle, northwest Texas, and eventually into southern Oklahoma by the morning of May 11th. Now, this convection was forecast to dissipate pretty quickly, but it actually hung on for quite a while until about midday or just early afternoon before it finally dissipated just east of the I-35 corridor there in southern Oklahoma. Now, as we know, ongoing convection in a target area can have negative impacts on the environment for severe weather later on. Of course, the ongoing convection can sap instability, and you have to rely on air mass recovery behind the morning complex to allow destabilization to happen and robust storms to be maintained. And if you don't have enough time for that, then you may not be able to realize the full potential of the environment as far as severe weather goes. Now, if you have morning storms that move out 8, 9, 10 a.m. and you have clearing behind it, usually that's not too much of an issue. You have plenty of time for destabilization behind the complex. But as you can see here, the morning complex across southern Oklahoma took its time to dissipate and actually stayed pretty strong for quite a while into southern Oklahoma. This is 15, 16, 17Z, 18Z. It finally dissipates. That's 12:01 p.m., so early afternoon, and it was causing a little bit of uncertainty to be added to the forecast, especially for us, as we had woken up in western Kansas and we were driving south for our chase into the 10% hatched area in southern Oklahoma. So it was a little bit worrisome that early complex may hamper things, but it became pretty clear early on that it was not going to be too much of an issue. Here's our satellite imagery, a little bit of a wider view here, but shows the situation pretty well. Here is our ongoing complex. This is at 18Z, so 1 p.m. Central Daylight Time. Ongoing complex in its dissipation phase. You can see quite a few clouds behind it as well. Now you'll notice, though, that we have pretty rapid clearing behind that. Those low clouds really start to go away pretty quickly. We do have some of those cloud streets that you can see there indicative of low-level stability, but those were quick to erode, and storms were able to fire in southern Oklahoma pretty nicely along the dry line. So not too much of an issue, and thanks to that clearing from some dry air intruding in from the west, we were able to get clearing pretty rapidly behind the initial complex and destabilize nicely into the afternoon hours. We'll take a look at our surface data now as well to back that up. We'll start at 12Z, and you can see low to mid-60s dew points across much of Oklahoma, with our better dew points, 60s into the low 70s down here in central Texas. Now, of course, ongoing convection in the morning can hamper moisture return into this region, so there was a little bit of a question whether or not we would see those 70s, upper 60s and 70s dew points make their way east of the dry line here into southern Oklahoma. But you can see here on our progression of the surface data that we have a little bit of some wonky readings here due to that complex going on in southwest Oklahoma into the late morning, early afternoon. But behind that, surface temperatures rebound pretty quickly. You can see we drop into the low 60s here in western Oklahoma. Surface temperatures rebound very quickly behind that complex into the mid to upper 70s, even low 80s by 3 p.m. So not much of an issue as far as low-level temperatures go, and we also were able, thanks to that pretty strong low-level flow ahead of that surface low in southeast Colorado, to advect those 70s dew points up into southwest Oklahoma and really destabilize the atmosphere in the wake of the ongoing morning convection. Now, an interesting feature was the outflow boundary that was trailing behind the ongoing complex. So you can see here a pretty clear outflow boundary, 89 degrees here in northwest Texas, 85 at that station, with mid-70s here up along the Red River into southwest Oklahoma. So clearly an outflow boundary was left behind by that dissipating complex. Given strong heating on both sides of the boundary, that was able to retreat northward on that low-level southerly flow, and it took its position by storm initiation time here in southwest Oklahoma. You can see it washed out a little bit, 80, 78, 78, 85, so a little bit weaker, a little bit more washed out boundary there, but still an outflow boundary nonetheless. We can pinpoint our dry line as well. Dew points in the 30s here in the Texas Panhandle, Texas South Plains, with dew points in the 60s and then 70s here in southwest Oklahoma. So our dry line was somewhere in here. You can also see a wind shift, winds out of the southwest in the Texas Panhandle, southwest Oklahoma, with winds more out of the south or even southeast across south central Oklahoma. So our dry line was somewhere in this vicinity right in here. Of course, we know what happens at the intersection of boundaries, dry line outflow boundary intersection. That was our initial storm formation location there near the Lawton Fort Sill area, just south of that area. Storms initially fired before storms were able to fire along the dry line farther to the north near Oklahoma City. Temperatures were able to rebound there as well. Upper 60s or mid 60s there at about lunchtime, increasing into the upper 70s by 5 p.m. there at Oklahoma City, 77 over 69. So a nice environment was advecting its way east of the dry line for additional storm development near the Oklahoma City metro area by early evening. Just a couple of observed soundings before we go into our radar and proximity sounding analysis. This is the 12Z or 7 a.m. Central Daylight Time Norman sounding on May 11th. Right off the bat, you'll see we have a little bit of elevated instability to deal with here. And if we go to Fort Worth, there's actually quite a bit more. Most unstable cape at about 1,100 joules per kilogram, mixed layer cape at about 800 joules per kilogram. Quite a bit of elevated instability to keep that morning storm complex going. That was part of the reason why it was able to sustain itself for quite a while across southern Oklahoma. But back to the Norman sounding, in contrast with the April 19th event, you won't see as significant of an elevated mix layer as we had on April 19th. Maybe a little bit of a semblance of the elevated mix layer there between about 500 and 700 millibars, but overall not too much elevated mix layer to speak of. A little bit of a moist layer, not very deep at all though, doesn't extend that far into the atmosphere off the surface, a little bit of drier air above that. You'll notice the hodograph, though, is quite small, only 15 knots of 0 to 6 kilometer shear at this point. We were still waiting for that trough to eject into the southern plains, but the hodographs would not lengthen significantly throughout the day, and that would have significant implications on what forecasters were expecting the characteristics of these tornadic supercells to be. And we'll get into that when we do our proximity sounding analysis in a few minutes. Now, of course, our main concern was what was the atmosphere going to look like between the 12Z sounding and the atmosphere behind the morning storm complex. And the NWS Norman office did release a midday balloon at 21Z, 4 p.m. Central Daylight Time, and there was no obvious issues at all from that morning storm complex. By 4 p.m., we had about 2,500 joules per kilogram of mixed layer cape, so pretty large instability had built back in. Thanks to continued moisture advection at the surface, you'll see that low-level moisture had increased 78 over 70 now, dew point of 70 there at Norman at 4 p.m. Central Daylight Time. So strong, low-level warm moist advection behind the morning storm complex, and all that clearing had helped that instability really rapidly build back in. And by this point, we were completely uncapped, so anywhere where surface convergence was maximized, i.e. at the intersection between the dry line and the remnant outflow boundary, storms were going to have no issue going up pretty rapidly. You will notice maybe a slight difference between the April 19th event is that the low-level and mid-level lapse rates were not quite as steep as on the April 19th event. And that may have led to slightly less robust updrafts, a little bit more of a large to significant hail threat with the April 19th event. If we go back to our 19Z sounding from Norman on April 19th, you will see that very nice, well-mixed boundary layer, steep lapse rates in the low levels, steep lapse rates in the mid levels, thanks to that elevated mixed layer. So significant hail was a big threat with the April 19th event. You will see quite a few more hail reports here across central Oklahoma. Those green and black dots are your hail reports there in central Oklahoma, compared to our May 11th event, where it was mostly tornado reports, a few big hail reports, but the biggest threat across central Oklahoma was our tornado threat there with the May 11th event. So a slight difference, still able to get robust storms out of this environment on May 11th. The hodograph, as you'll see here, did remain quite small, even though deep layer shear was increasing, 0 to 6 kilometer shear at 34 knots, effective shear at about 30 knots. So deep layer shear was increasing as that 500 millibar trough moved in. Those mid-level winds increased to about 30 to 40 knots. But again, the hodographs remained small through much of the day, and we'll go over the implications of that in just a second. Storms did not have trouble initiating in this environment, but they did struggle to maintain themselves. We saw our first attempts at storm initiation not long after the initial morning complex had moved past the I-35 corridor. We saw our first storm attempts near the Wichita Falls area in northwest Texas. They tried to do some interesting things, but just couldn't quite sustain themselves. Our first real attempt at a legit supercell was up here near the Randlet area in far southern Oklahoma along I-44. See a very nice supercell here. We thought this was going to be the storm of the day, developed a very nice appendage there pretty quickly, tried to grab and latch onto that boundary right at the dryline outflow boundary intersection. By this time, the outflow boundary had retreated northward just a little bit. And again, along that dryline outflow boundary intersection was where surface convergence was maximized. And we got our first legitimate storm of the day near that area. And again, we thought this was going to be the storm of the day, tried to latch onto that boundary, but eventually it struggled. This was the first storm we pulled up on as we got into the target area. And you can see it kind of rockets to the north, eventually loses its appendage. I think it may have started to move away from that maximized surface convergence near that dryline outflow boundary intersection. Perhaps a little bit of lingering capping, maybe a little bit more farther south here, closer to the Red River. And we arrived at this storm and watched it just die in front of our eyes. It got choked off and just shredded. But we did see some storms firing back to the north. We were a little discouraged at this point, but if you know the tornado history of this part of the world, I like to call this the I-44 rider. Storms will fire along the Wichita Mountains out here in southwest Oklahoma or even near Lawton and just ride up that I-44 corridor in or near the Oklahoma City metro area. So we did see these storms going. We decided to haul it back north, and we were getting a little bit nervous that these storms may eventually come pretty close to the Oklahoma City metro area. We take a little bit of a closer view. These became supercells fairly quickly. You see that nice supercell shape there, especially with the northern storm there near Chickasha. And you'll see as they go to the north, a little bit of a messy, somewhat semi-discrete mode there. You still see some discrete updrafts in there. And our first tornado of the day actually appeared near Tuttle. This was probably buried back in the rain with this northernmost supercell there. We were still trying to haul back north on I-44, so our eyes were set on this just to the south. We thought it would probably do the exact same thing, and that it did. It started to get a nice appendage on it as it approached Newcastle, really started to tighten up, and that is when we had our first couple tornadoes, those brief tornadoes near Newcastle. Very well-defined hook echo with that storm as it approached Newcastle. Quickly became outflow dominant, though, after it produced those tornadoes. You see the outflow boundary there on radar, that shear signature there. The greens going toward the radar, reds going away from it. Lots of greens going out from that storm there. So that indicates a lot of outflow production. So we dropped to the southern storm, which was trying to take on and do the exact same thing that northern storm did, and it did that in spades. You see it start to develop a nice hook echo there as it approached Cole. And it eventually produced a pretty notable tornado near Cole, classic hook echo there. And you'll see as it approaches Goldsby, it does a classic handoff. So our original circulation starts to occlude off to the north or northwest, aka deviant motion. We'll talk about that more in a second as it relates to the wind profile. It starts to go toward the north. The original hook goes into the forward flank of the storm, and you get new rotation out on the tip of the hook here out to the east. And that's exactly what we got. That original circulation occluded just to the west of Goldsby, and then we got a new circulation right over the town of Noble that produced some damage. Very well-defined hook there as it moved through Noble, producing an EF1 tornado there. Tried to wrap up again as it got to the southeast side of Norman, just couldn't quite get it done. I believe we had one or two more brief tornadoes as it moved off to the east, but I think by this point the capping started to work its way back in. These storms were fairly small, more susceptible to the capping. We'll talk about supercell size as it relates to the wind profile here in a second as well. But overall, the event was pretty much over by 9:30, 9:45. We did have an additional tornado near the town of Maud, well out to the east of the Oklahoma City metro, but that was about it for the noteworthy tornadoes in this event. We did have a couple supercells try to fire up well out ahead of those dryline storms. You see here a couple of those echoes, perhaps associated with those initial attempts near Randlet. They stayed alive. They held on by a string. Here are your dryline storms approaching the Oklahoma City metro, which is right in there. That would eventually produce the Newcastle and Cole tornadoes. But you see those storms just try to hang on, and we got additional development, just enough forcing out ahead of those dryline storms to produce a couple supercells out ahead. They tried to wrap up, but could not quite produce any tornadoes, despite being very much isolated, a little bit more isolated even than the other storms, at least initially. So that was a little bit surprising there. But the main tornado producers definitely came from the storms along the dry line. All right, let's go through a progression of RAP model proximity soundings. Once again, these were taken from Purcell, Oklahoma, just south of the track of the main supercells on May 11th. So we start off at 12Z. Once again, very weak instability at this point, just enough to keep those storms in southern Oklahoma going, perhaps a little bit stronger instability to the south. But here at Norman, very weak instability, very meager hodographs throughout the entire atmosphere, as that trough had not quite kicked in yet. As we go through the day, though, it's pretty easy to see when that destabilization really starts to take place behind that morning storm complex and cloud cover. Here at 18Z, we have about 300 joules per kilogram of mixed layer CAPE. And then over the next couple of hours, we rapidly increase that to well over 2,000 here at 21Z, 4 p.m. as storms were initiating about 2,400 joules per kilogram of mixed layer CAPE, fully destabilized here. And then in the next couple of hours, here at 23Z, 6 p.m. Central Daylight Time, 3,400 joules per kilogram of mixed layer CAPE. So we really started to see destabilization occur very rapidly behind that morning storm complex, thanks to a number of things. Of course, low-level warm moist advection here at 18Z, dew point at the surface at 63 here at Norman, and then a very rapid transition into the low 70s dew points at the surface here at Norman, or at Purcell. So strong low-level warm moist advection, some dry air working its way in. You can see the separation between the red profile, the temperature profile, and the green dew point profile as you go up in the atmosphere. An intrusion of some dry air behind the morning complex helped really erode that cloud cover behind the morning storm complex and allow for full surface heating from the sun. And so a very strong thermodynamic profile. Again, not quite as strong of lapse rates here throughout the column as we saw on the April 19th event, but still more than adequate, and destabilization happened pretty rapidly and pretty efficiently to get us a thermodynamic environment favorable for robust convection. Hodographs, once again, remained small throughout the day. You'll see here 13 knots of effective bulk shear, 10 knots of 0 to 6 kilometer bulk shear at 12Z. Finally, that trough starts to work its way in by about late morning, 16Z, 11 a.m. We bump up that 0 to 6 kilometer shear to about 36 knots there, which is in the range for supercells, and that maintained itself through the evening. Upwards of about 35 to 40 knots of effective shear, 0 to 6 kilometer shear there at 23Z. So definitely an environment favorable for supercells. Not necessarily strong tornadic supercells as was forecast, although this was definitely not an environment to scoff at. 3,400 joules per kilogram of mixed layer CAPE with about 200 meters squared per second squared of effective storm relative velocity. Definitely a hodograph skew-T combo favorable for tornadic supercells. But if you were to show me the tornado probabilities from each day, April 19th and May 11th, without the date, I would have told you the 10% hatched area was for April 19th and the 5% was for May 11th. Because this is, certainly not a strong tornado type of environment. Definitely an environment favorable for tornadic supercells, but not necessarily for strongly tornadic supercells here on May 11th. April 19th, however, though, same amount of instability. Again, a little bit steeper lapse rates aloft, so a little bit more robust updrafts. And that hodograph definitely a little bit more favorable for strong tornadoes with over 300 meters squared per second squared of effective storm relative velocity there. Nice curvature in that hodograph. Favorable for strong tornadoes there on April 19th. Not so much on May 11th, although, again, definitely not an environment to sneeze at. Now, we've talked a lot about the hodographs here in this discussion, staying a little bit on the small side, and that has some implications on the storm behavior. Now, so we can use a couple of techniques to figure out the things like supercell size and the venting of precipitation away from the updraft region. All of this information is contained in Cameron Nixon's amazing hodograph page here on his website. I'll put a link to this in the description box below. But let's go ahead and start and really dive into these hodographs. We'll start by the fact that these hodographs remained quite small throughout the day, throughout the entire atmosphere. So we'll use our 0Z hodograph from Purcell, our proximity hodograph. At this point, storms were starting to take off. Those supercells were getting ready to produce tornadoes within the next hour or so. So first thing we can look at is called storm relative outflow. I'll abbreviate storm relative by SR, but storm relative outflow, generally above about 6 kilometers above ground level. So that's the yellow and teal portion of the hodograph. Storm relative outflow, all we do to find that out is we draw a vector from our storm motion, which is right in here, to our level of interest on the hodograph, generally, again, above 6 kilometers or so. The larger the storm relative outflow, the greater the venting of precipitation is away from the updraft. So if you have a case where you have very strong winds aloft and a very long vector leading from your storm motion to your hodograph, that indicates a large storm relative outflow, and therefore precipitation is going to be vented away from the updraft region, and generally anything above about 40 knots, a deep layer of 40 knots or more of storm relative outflow above 6 kilometers is considered good for more low precipitation supercell types. When those vectors are shorter, i.e. when your storm relative outflow is much weaker, that promotes less efficient hydrometeor or precipitation venting away from the updraft and more high precipitation storm modes. And you'll notice pretty easily from our using this technique here that these vectors are not very long at all, maybe 10 to 15, 20 knots at most through much of that layer above 6 kilometers. And these were showing up, this was showing up on forecast soundings as well. So we were expecting a very much a high precipitation storm mode with these supercells. And so any tornadoes were expected to be quite shrouded in rain, given a lack of precipitation venting away from the updraft region of the storm. And the Storm Prediction Center actually mentioned this in their Day 1 convective outlook. This is the 13Z Day 1 outlook from May 11th. And they mentioned the upper level wind fields will weaken with height, and the bulk of the hodograph structure will consist of enlarged curvature from 0 to 3 kilometers. This suggests supercells should tend toward an HP character with a slow-moving cluster type evolution. So the Storm Prediction Center was on board with this as well. Lots of models were showing these hodographs being much smaller and storm relative outflow being very poor for very poor hydrometeor venting away from the updraft. But if you recall, some of the video footage I showed, the tornadoes were not very shrouded in rain at all. This was the Newcastle tornado here, as well as the Cole tornado, very much visible for its entire life cycle. So there had to be something compensating for that HP character in the lack of hydrometeor venting away from the updraft. We can go back and use the storm relative inflow to do that. Storm relative inflow is basically just the opposite of storm relative outflow, this time in the lower levels of the atmosphere, generally below about 1 kilometer aloft. And the larger and storm relative inflow modulates the amount of mass that is being taken in by the supercell. So larger storm relative inflow, meaning a longer vector from your storm motion to the hodograph in the lowest 1 kilometer of the atmosphere. Larger storm relative inflow in the low levels indicates that more mass is being taken in by the supercell, and therefore this dictates you'll have much larger supercells in size. When your storm relative inflow is smaller, generally below about 25 knots or so, that means that not as much mass is being taken in by those supercells, and therefore you'll have much smaller, perhaps even mini supercells. So our storm relative inflow, and I'll use the 22Z per cell sounding to illustrate this, that at least initially, storm relative inflow with these storms was fairly weak. We'll draw our vectors from our storm motion to the low levels of the hodograph, and these vectors were very, very short, perhaps 10, 20, maybe 20 to 25 knots of storm relative inflow in that lowest kilometer of the atmosphere. Therefore, less mass being taken in by these storms on May 11th, therefore these storms were much smaller. Smaller storms do not produce as much precipitation. So therefore, even though the hydrometeor venting or precipitation venting away from the updraft was very, very poor due to weak storm relative outflow aloft, there just wasn't that much precipitation being produced by these storms in general. So therefore, that compensated for that HP character that was forecast for these storms, and therefore we saw much more visible tornadoes than what was expected. And we can even draw this on our radar imagery. So this is our Cole supercell from April 19th. We can estimate our precipitation shield, if you will, from the north side of the forward flank to the tip of our hook, or the base of our hook. It goes from about Moore, Oklahoma to Dibble right there. So if we go back to our radar imagery for the May 11th event, I'll fast forward this to when the storm was right over the Cole-Goldsby area producing the tornado. So if we were to draw our April 19th, I'll draw it in pink here, our April 19th supercell, it would look something like this, with our hook down there by Dibble and our forward flank precipitation core extending up toward the Moore area. So you can see that the April 19th supercell was much, much larger than our May 11th supercell. That was because we had much less mass being pulled into the supercell on May 11th, much less storm relative inflow for much smaller storms, not quite producing as much precipitation on the May 11th case. We can even look at our 23Z per cell sounding from April 19th to see that the storm relative inflow was a little bit larger. So you see here maybe 10, 20, 30 knots or so storm relative inflow on April 19th compared to much smaller, at least initially, on our much smaller storm relative inflow, at least initially, on our May 11th day. Maybe 10, 20 to 25 knots, at least initially. We did see a slight increase in storm relative inflow going into the early evening hours on May 11th. See a little bit of a lengthening of those vectors, still on the lower side, and we maintained a little bit more of a smaller size to the supercells as they moved closer to the Oklahoma City metro. And one last note on the deviant tornado behavior, especially of the Cole-Goldsby tornado. If you recall, the Cole-Goldsby tornado started to occlude very much toward the north as it handed off to the new circulation near Noble. And so we can use our same deviant tornado motion technique that we used for the April 19th case to figure out how deviant the tornadoes were likely to be on the May 11th day. So we'll use our 0Z per cell proximity sounding from May 11th to do our technique here. So once again, we find first our mean wind in the lowest 500 meters of the atmosphere. That's the midpoint of this pink line there. Then we plot our storm motion vector, and then we take the average of those two. So right in the middle of those two is going to be our deviant tornado motion vector. So the deviant tornado motion much more to the northeast. Our storm motion, I'll draw that in blue here. Storm motion much more to the east-northeast, and our deviant tornado motion vector much more to the northeast. So not quite as drastic a case as the April 19th case was, in which you had tornadoes deviating almost to the north and then back to almost the northwest at times. Here you had a little bit more subtle deviant tornado motion vector, but still enough to perhaps cause some issues if you were on the north side of these tornadoes as they were occluding, especially that Cole-Goldsby one. If you were on the north side of that tornado, you'd be in a little bit of trouble as it occluded and perhaps did a little bit of orbiting around the main parent mesocyclone. I'll go back to our imagery from the NWS of the tornado path. You see there a little bit of deviance there, of advection by the storm relative wind, and then perhaps a little bit of orbiting around the parent mesocyclone as it did kink back around to the northwest at the very end of its life cycle. So deviant tornado motion not quite as pronounced as on the April 19th case, but enough to raise some eyebrows, if you will, if you were on the north side of this tornado. And again, we did this technique as we were forecasting for this day and noted that there could be a little bit of deviant motion. Again, not quite as pronounced as April 19th, but enough to where we wouldn't want to be on the north side of the tornado as they were occluding. So that's going to do it for this video. Hope you enjoyed the comparison between the April 19th and May 11th events. Definitely two events that put Oklahoma back on the map, if you will, as far as tornadic activity goes during the spring. It's been, again, quite a drought for Oklahoma. We've had a few tornadic events here and there, but nothing really impacting areas close to the Oklahoma City metro area. It felt like OKC and its surrounding areas were long overdue for a couple of big events, and 2023 certainly provided with the April 19th and May 11th events. So if you have any comments or questions, please put them down in the comment section below. I'm happy to get back to you, and thanks for watching. We'll see you in the next video.